So far, solved equations are with the format y is equal to the function of x. However, most equations involve mixed variables. Find out how we differentiate such equations here in differential calculus. Say we have 3x squared minus 2x minus y is equal to 0. By transposing y to the other side, we have 3x squared minus 2x is equal to y. If y is a function of x, or if variables are completely separated, then we call this function explicit. For the other equation, x squared plus y squared is equal to 2 times x times y. We do the same attempt of separating variables, but we will be getting nowhere, so we can conclude that in equations where we have the functions of x and y are equated to 0, these are referred to as implicit functions. Before starting with differentiation, let's check out how to identify a function, whether it is implicit or explicit. The first equation being x squared y plus y is equal to the root of x plus 1 has variables x and y all over. So we attempt to separate them by transposing. But before doing so, we can factor out y from the two terms on the left, leaving us with y times the quantity of x squared plus 1 is equal to the root of x plus 1. Then since we only have one y left, we can place the other terms with it to the other side, and that is by division. So we get y is equal to the root of x plus 1 all over the quantity of x squared plus 1. Note that y is already expressed in x, thus the equation is an explicit function. Next is x squared minus 2y cubed plus 4y is equal to 2. Just the same, we collect similar variables on either side of the equation, then factor them out. X on the right side is isolated, but even if we factor out y from the left, we are left with 2y squared minus 4, which is still got a y, and even if we place the binomial to the other end, we still can separate x from y. Thus, this equation is an implicit function. Now, what are the steps in working on implicit differentiation, or that is differentiating implicit functions? First is to differentiate all terms in both sides of the equation, commonly with respect to x, regardless of what the variable is. After which, isolate all terms with dy all over dx to one end, and all the other terms move to the opposite side of the equation. Third, extract y prime or dy all over dx from the left side of the equation, then solve for it, and that is simplifying the equation for it. For the first example, we are tasked to find dy all upon dx from the equation y cubed plus y squared minus 5y less x squared is equal to negative 4. The first step is to differentiate all terms, and that is by plugging d all over dx to each of them. So with the various differentiation rules, we get the derivative of y cubed as 3y squared, then by the chain rule, we connect dy all over dx. This will be continued with the derivative of y squared from the second term, giving 2y times dy all over dx. Next is the derivative of negative 5y. What we do is to place out negative 5 from the derivative of y with respect to x. Then we have the derivative of negative x squared, which turns out as negative of 2x times the derivative of the variable x, with respect to x. For the right end of the equation, we have the derivative of negative 4 with respect to x, and since negative 4 is a constant, its derivative turns out as 0. With the resulting equation, remember that we can simplify dy all over dx as y prime, and also dx all over dx as 1. So for the second step of collecting terms with y prime, all we needed to do is to transpose negative 2x to the other side, where our equation turns out as 3y squared y prime plus 2y y prime minus 5y prime is equal to 2x. For step 3, extract y prime from all the three terms on the left, making the equation y prime multiplied by the quantity 3y squared plus 2y minus 5 is equal to 2x. Then with only one y prime observed, we can solve for it by cross multiplication, where we place the quantity with y prime down to divide the term on the right. So y prime is taken as 2x all upon 3y squared plus 2y minus 5. The second example has the equation to be differentiated implicitly as the square of x minus y is equal to 2ax. So step 1 is to add d all over dx to the square of x minus y and also to 2ax. By differentiation rules, the derivative of the square of x minus y turns out as 2 times the quantity of x minus y, and then again take the derivative of each term, marking dx all over dx minus dy all over dx. The other side will become the constant 2a times dx all over dx. Let's do away with the long d's, so we convert dx all over dx into 1 and dy all over dx as y prime, making the equation shorter as twice of the quantity x minus y multiplied by the other quantity 1 minus y prime is equal to 2a. Next is to isolate y prime, and because it is included in a quantity, the whole 1 minus y prime is placed in the left side, and the rest of the expression turned as denominator in the right end of the equation. We cancel out the 2's to have 1 minus y prime is equal to a all upon x minus y. Further isolate y prime by transposition to have y prime is equal to 1 minus a all over x minus y. Then to solve for dy all over dx, we make a unified denominator by taking the LCD and then collect the numerators, so the final equation is y prime is equal to x minus y less a, and this is all upon x minus y. Let's have another example whereby the equation will be ending with 2ay as the previous one ends with 2ax. Let's check what happens with the derivation with a switch of variable on one side. Again, start with adding d all over dx to each term, and then work on the differentiation. The derivative of x minus y squared turns out as 2 times the whole quantity of x minus y. Then take the individual derivatives of each term, that is derivative of x with respect to x minus the derivative of y with respect to x. Again, simplify dx upon dx as 1 and dy upon dx as y prime, making the equation 2 times the quantity of x minus y multiplied by 1 minus y prime is equal to 2a y prime. Next, we separate terms with y prime and move all others to the opposite side. Cancel out 2 and separate the terms in the left, making 1 all over y prime minus y prime all over y prime is equal to a all over x minus y. By the expansion, we simplify the equation with only one y prime, and that is with the equation 1 all over y prime minus 1 is equal to a all over x minus y. Transpose 1 to the right for the third step of factoring out y prime to the left, then solve for y prime by taking the least common denominator of both terms on the right, and that is by making an equivalent fraction with 1. Then now, we have 1 all over y prime is equal to x minus y plus a all over x minus y. Since y prime is at the denominator, we flip parts to get y prime is equal to x minus y all upon the quantity of x minus y plus a.